Chapter 1. MCP Middleware Integration Fundamentals. Command Anatomy, Claude vs Hermes YAML, and Server Registration. The Model Context Protocol has emerged as the standard bridge between large language models and external tool ecosystems. Our starting point, Claude MCP at ROS MCP UVX ROS MCP transport equals STIO. Three semantic layers form the foundation. Layer 1 Registration Declaration. Claude MCP at ROS MCP defines the CLI entry point, the MCP management subcommand, and the server identifier. This tells Claude about a new tool provider. Layer 2 The double dash separator is the mandatory delimiter isolating CLI flags from server launch arguments. Without it, the shell would misinterpret UVX and ROS MCP as Claude's own parameters. Layer 3 Launch Command. UVX ROS MCP transport equals STIO. UVX runs Python packages without permanent installation. ROS MCP exposes the full ROS2 surface. STIO keeps communication local, zero network overhead. Claude vs Hermes, two paradigms. Claude's imperative CLI gives one-line registration but scatters config between .mcp.json files. Hermes uses declarative YAML with a single source of truth in config.yaml, version control friendly. Hermes YAML configuration schema. Top-level MCP servers key. Named entries with command, absolute path, args, array, enabled, toggle, timeout, seconds, and optionally env block. Each field maps to a Claude CLI equivalent. Scope management. Claude defaults to project scope.mcp.json. Hermes supports global config.yaml plus project-level.hermes.yaml overrides. Understanding this prevents missing server mysteries when switching directories. Community baseline. For focused developers, 1 to 3 MCP servers is normal. Each adds 500-2000 tokens overhead. More servers means slower responses and higher RAM. Choose deliberately, not maximally. Key takeaway. MCP registration has 3 layers. Claude and Hermes represent imperative CLI versus declarative YAML. Scope awareness and overhead management are essential. Next, configuring ROS MCP for the first time. Chapter 2. Troubleshooting in practice. From a 120-second timeout to a successful connection through a 3-layer root cause diagnosis. Starting point. The user's config.yaml has no MCP_server's root node, only an unrelated auxiliary block. Step 1. Manually add the ROS MCP server block at the bottom of the config file. First attempt. Command, absolute UVX path. Args, ROS MCP, transport equals STIO. Enabled, true. Timeout, 120. Running/reload MCP in Hermes. Result, no MCP servers connected. Timed out after 120 seconds. Layer 1 diagnosis, missing ROS environment. Hermes subprocess is not equal to interactive shell. No inherited ROS environment variables. ROS MCP crashes before sending any MCP handshake. Fix, inject ROS environment into the config. Iteration 1. Adding env, ROS_distro equals humble, ROS_version equals 2, Python path, ROS bin in path. Timeout raised to 180. Reload. Still fails. Something deeper is wrong. Layer 2 diagnosis, Stout protocol contamination. FastMC prints an ASCII color banner to Stout at startup. MCP protocol mandates Stout carry only JSON RPC frames. Non-JSON text corrupts handshake parsing. The breakthrough fix, bash wrapper. source/op/rows/humble/setup.bash injects full ROS runtime. 2/dev/null redirects stare, eliminating the ASCII banner. Timeout 180 provides adequate initialization window. One config change resolves both layers. Success. /reload MCP now shows added ROS MCP. 35 tools from one server. Reconnected ROS MCP. Agent updated 63 tools total, 28 built-in plus 35 ROS MCP. Connectivity verified. Hermes MCP test ROS MCP connected, 758 milliseconds, 31 tools discovered. Full ROS2 introspection, topics, services, nodes, parameters, actions, network diagnostics all operational. Root cause summary. Layer 1, subprocess ENV isolation source ROS. Layer 2, stout pollution redirect stare. Layer 3, insufficient timeout raised to 180s. Key takeaway. AI agent subprocesses need explicit runtime injection. Protocol output formatting is a stealth failure vector. Bash wrappers provide the most reliable integration path. Next, live robot simulation testing. Chapter 3. Simulation testing, TurtleSim natural language control. ROSBridge nodes, natural language to MCP tool invocation, live robot interaction. Probing the ROS graph. With ROS MCP connected, we ask, list all running ROS2 nodes. Hermes invokes get_nodes via MCP, wrapping ROS2 node list. 3 standard ROSBridge backend nodes appear. The ROSBridge stack. /ROSBridge_WebSocket, WebSocket bridge for MCP left-right arrow ROS communication. /ROSAPI, introspection APIs, nodes, topics, services. /ROSAPI_params, ROS2 parameter read/write. These are required infrastructure, not user nodes. Deeper probe. Show all active ROS2 topics and their message types. Hermes calls get_topics. For system topics /client_count, /connected_clients, /parameter_events, /ROSOut. All standard ROSBridge channels, the ROS graph connection is confirmed. Where are the robot topics? No /cmd_vel, /scan, /odem, /camera /image_raw. Not a bug. MCP only sees actively running topics. No simulation launched yet. Infrastructure ready, awaiting payload. Launching TurtleSim. ROS2 run TurtleSim_node. A turtle on a blue canvas. New topics appear /turtle1 /cmd_vel, velocity, /turtle1 /pose, position feedback, /turtle1 /color_sensor, pen. Verification. Rerun show all active ROS2 topics. Robot topics now appear alongside ROSBridge infrastructure. Hermes via ROS MCP has full visibility into the live ROS2 graph including simulation nodes. Integration confirmed. Natural language control. Publish a message to /turtle1 /cmd_vel with linear.x equals 2.0. Hermes translates natural language publish_once MCP call geometry_msgs /twist ROSBridge ROS graph. The turtle moves. No tool names, no CLI syntax. The mechanism. User natural language Hermes LLM MCP tool selection ROS message construction topic publish ROSBridge ROS graph TurtleSim callback turtle moves. Sensor feedback closes the loop via MCP subscriptions. Workflow transformation. Engineers describe behavior in natural language instead of writing C++/Python publisher nodes. Hermes handles ROS primitive translation. Development feedback loop shrinks from hours to minutes. Key takeaway. ROS-Bridge is the communication backbone. MCP exposes ROS as discoverable tools. Natural language is the programming interface. TurtleSim validates the full stack. Next, scaling to real hardware with Jetson Xavier. Chapter 4. Robot System Architecture. Host machine, Jetson Xavier, distributed ROS2 deployment, and edge inference. Two-tier architecture. Host machine, powerful desktop/server running Hermes, LLM, high-level planning. Embedded computer, Jetson Xavier on the robot running low-level control, sensor drivers, real-time safety loops. Why the split? LLMs need significant GPU memory, impractical on mobile robots. Jetson Xavier provides efficient edge inference at 10 to 30 watts, ideal for battery-powered platforms. Clean separation of heavy AI from real-time control. ROS-Bridge is the bridge. Running on host or robot, ROS-Bridge exposes the entire ROS2 graph over WebSocket. Hermes ROS MCP ROS-Bridge ROS2 topics on the robot. Commands flow from natural language to motor control. Jetson onboard stack. Sensor drivers, cameras, LiDAR, AMU, published to ROS2 topics. Perception nodes, potentially VLM-based, process feeds. Motor controllers subscribe to /cmd_vel with hard real-time deterministic latency. Separation of concerns. Host handles AI reasoning plus user interaction. Jetson handles time-critical perception plus control within tight latency budgets. Standard ROS2 topics over network, transparent to application layer. Independent development and testing. VLM and VLA, the next frontier. Vision language models describe scenes semantically. Visual language action models output robot actions directly from pixels. Lightweight VLM on Jetson for onboard obstacle detection, a practical first step. MCP makes it programmable. From Hermes, query Jetson nodes, inspect topics, read parameters, publish test commands, all natural language. No SSH, no ROS CLI memorization, no context switching. Persistent MCP connection amortizes setup cost. Typical workflow. Start Hermes query robot nodes, check sensor topics, send test velocity, monitor pose feedback, adjust parameters iteratively. All from one chat interface. Development feedback loop, minutes, not hours. Network considerations. ROS-Bridge uses WebSocket over TCP. Wi-Fi needs adequate bandwidth plus low latency. ROS2 DDS auto-discovers across network. Production security, always use TLS or VPN for ROS-Bridge on untrusted networks. Key takeaway. Two tiers separate AI from real-time control. ROS-Bridge plus MCP equals unified natural language interface. Jetson Xavier equals efficient onboard edge AI. Next, VLM and VLA model integration for autonomous behavior. Chapter 5. AI model integration. VLM, VLA, and the future of robot intelligence. MCP as the universal model robot bridge. Vision language models, paradigm shift. Traditional CV detects predefined classes. VLMs describe arbitrary scenes in natural language. Show a VLM an image, a red box on a table, next to a blue cup, person approaching from the left. VLM options. Cloud, GPT-4V, Claude 3 Vision, heavy hitters for offline understanding. Host, LLVA, CogVLM open source alternatives. Jetson Edge, quantized Florence 2 or mobile VLM, real-time at 15 to 30 FPS. Visual language action, closing the loop. VLA takes pixels in, outputs robot actions, joints, gripper, velocity. RT2, Google DeepMind, Octo, UC Berkeley, OpenVLA, Stanford, trained on massive robot demonstration datasets. Integration architecture. VLM on Jetson captures frames, generates scene descriptions, publishes to ROS2 topic as string. Hermes subscribes via MCP, uses description for high-level planning. Perception to cognition pipeline. Reactive VLA on Jetson. Camera frame and velocity command out, all within 50 to 100 milliseconds control loop. Dynamic obstacle avoidance, grasp adjustments, navigation corrections. No waiting for host LLM. Safety critical response times guaranteed. MCP, the universal bridge. VLM scene descriptions, MCP subscription, Hermes reasoning, MCP publish robot action. Entire perception to action loop flows through natural language and standard ROS2 primitives. One protocol, end to end. Concrete example. VLM detects obstacle, publishes warning, Hermes receives via MCP, LLM plans alternative path, Hermes publishes new trajectory via MCP, robot adjusts course. 0 custom code. Only configured MCP tools. Development advantage. Testing VLM prompts and VLA configs no longer requires writing ROS nodes. Engineers describe tests in natural language. Hermes sets up conditions via MCP. Results observed via MCP subscriptions. Hours become minutes. Limitations in future. VLMs can hallucinate scene descriptions. VLAs trained in labs may fail in unstructured environments. MCP STIO adds latency versus native DDS. Active research, VLM 3D spatial grounding, VLA sim-to-real transfer, MCP streaming. Looking ahead. LLMs plus VLMs plus VLAs plus MCP converge toward conversational robot programming. Engineers describe intent in natural language. AI stack handles perception, planning, control. MCP ensures every component speaks the same protocol. Conclusion, 5 chapters. MCP middleware troubleshooting, TurtleSim validation, distributed Jetson architecture, VLM/VLA integration. The future of robot programming is conversational, and the building blocks are already here.